Please get ready to welcome to the stage, Yin Song. Yes.
Thanks, Paul, for the great introduction of me. So, hi, everyone. My name is Yin Song. I'm a senior applied scientist from AWS. Just give you a little bit of background of me. I got my PhD in machine learning and data mining back in 2014. And I joined AWS in 2019. And I have been working in this machine learning and AI area for about 15 years. And today I'm going to talk about best practices for acquiring vector data in generative AI applications. So generative AI is a very hot topic, right? I bet you hear this all the way from the summit. But why we need vector data here, right? So let's start with a toy example here. Let's assume you are running a convenience shop. So you are selling a lot of interesting stuff here, right? As you can see the list. And you try to build an application to allow your customers to ask questions about your products interactively. The primary component for this application is foundation model. So foundation model are pre-trained model that allow you to perform a lot of different tasks, like using natural language. So the easiest way to use foundation model on AWS is by Amazon Bedrock. Good news is Amazon Bedrock is available in Sydney region now. So feel free to use it now. And the good thing of using Amazon Bedrock is you don't need to worry about managing infrastructure by yourself. Actually, you can call its API, and it's very convenient to use the API to call the foundation model. And also, you can choose a wide range of models from a wide range of model providers. For example, you can choose the Titan model provided by Amazon. You can choose the latest Cloud 3 model from Anthropic. And also, you can choose the Llama 2 from Meta. You just choose the right model for your use case. That's very convenient. Lastly, you can actually fine-tune your model, use your own data, so which is also very beneficial to your use case. If we use the foundation model directly to build the app, and if you ask questions about the product in our toy example, the foundational model probably doesn't know the answer to your question. So this is because foundation models are usually trained using the public available data. It don't have any knowledge about your specific products in our toy example here. To actually augment the capability of the foundational model, we usually use a framework called Retrieval Augmented Generation, RAG. So using RAG, actually you can integrate your knowledge base into the foundation model, and then your foundation model can answer questions specific to your knowledge base. A critical part of the RAG framework is vector embeddings. Basically, we translate all the unstructured data in your knowledge base into some kind of vector embeddings. Using these embeddings, we can actually perform similarity search and to find the relevant content or context to your questions. And then we send that along with your question to the foundation model, and then it can answer your question properly. So you may ask, why don't we just use some kind of text search? So this is because text search relies on the keywords. So using vector data or vector embeddings, we don't rely on any keyword. So we can do some kind of semantic search or semantic similarity search. So there's challenges with vector data. As I mentioned, we need to use some embedding model to actually transform your data into vectors. That usually takes time. And also, for modern embeddings, it's usually a little bit high dimension. Usually it could be over 1,500 dimensions. So think of using a 4-byte float to store every dimension, and then you need 6 kilobytes to store a sample of vector data. If you consider you have 1 million of such records, you need to have 5.7 gigabytes to store your data. You really need to consider how to store it. And another thing is you can't compress the vector data. That means it's even more challenging for you to actually store the vector data. Lastly, if you want to perform any queries or similarity search, actually you need to compare each dimension of the vector data. That will definitely cost a lot of time. So to overcome this challenge, we usually use some off-the-shelf vector database like PostgreSQL, as well as some embedding models from Amazon Bedrock. So this is how vector embeddings are typically used in an IAG framework. First, you need to prepare your data in the format. For example, format could be anything. Usually it could be the format in PDF. And then you split the document into smaller chunks. After that, you can call like embedding models. For example, the Amazon Titan embedding models on Bedrock to generate the embeddings and then store the embeddings into a vector store. So usually we will choose the PostgreSQL as a vector store. And then when the user asks questions, it actually transforms into embeddings and then query against the vector store to find the relevant context. After that, along with the question, the context actually will send into the large language model, and then the large language model can answer your question properly based on your knowledge base. To give you even more intuition on how it works, let's see a real demo of IAG application. Here we choose the Amazon. Here we choose the Amazon Aurora FAQ as our knowledge base. So it's very straightforward. The first, you need to find the FAQ document, PDF, and upload that into the application. And in the background, the application actually splits the document into smaller chunks and calls the Amazon Titan embedding model to generate the embeddings and store that in the PostgreSQL. And then you can ask questions about the Amazon Aurora. So the questions will be transformed into embeddings and then query against the vector database to get the context. And then it will be sent along with the question into the model and get you the proper answer about your question related to Amazon Aurora. You can see on the screen here, the large language model actually answers the question based on the knowledge base we provided here, which is very accurate and efficient. As we see in the demo, we choose PostgreSQL as a vector store here. Actually, using PostgreSQL as a vector store is a very popular choice. So the reason why we choose PostgreSQL, first, because we can co-locate our embedding data with your other data. For example, your application data, your transaction data together. And then you don't need to use another client library to query your data. You can use the same client library to query your data. And also, using PostgreSQL, it's very, very easy to integrate with other vector search systems, like OpenSearch. So that's why we choose PostgreSQL here. And the most important reason why we choose PostgreSQL is because it has an extension called pgvector, which supports the vector data type. And it provides two different kinds of search here: the exact nearest neighbor search and approximate nearest neighbor search, ANN here. And for ANN, it supports two different kinds of indexing here, RVF flat and HNSW. I will go to the detail about this very shortly. And as I mentioned, you can co-locate your embedding data with your metadata very conveniently on PostgreSQL. Lastly, it provides three different kinds of distance operators: L2 distance operator, cosine distance operator, and inner product distance operator. You can choose the most suitable one to your use case, so which is very convenient. Using PostgreSQL is very straightforward. So here is an example how you can get the 10 nearest neighbor to your vector 3, 2, 1. So you can just like you're writing a normal query. You just choose your distance operator. Like here we choose the L2 distance operator. And then you compare against your embedding column. And then to get the 10 nearest neighbor, you just use limit 10 as your keyword. As simple as that. So it's very straightforward to use pgvector to query your embedding data. You may ask, is that the end? The answer is no. To get optimized performance, you still need to know some best practices here. Let's start with the storage strategy first. So for the storage, before the deep dive, let's look at how PostgreSQL store data. So as many of you know, probably already know, for PostgreSQL, for less than 8 kilobytes data, it's probably store everything in line with the table. But for data greater than 8 kilobytes, it uses a mechanism called toast to store data larger than 8 kilobytes. Actually, by default, PostgreSQL will store everything over 2 kilobytes in an external toast table. That means for a 510 dimension vector data, it will automatically translate it into or toast it into external table. But how this impact our storage type? We know there's 4 storage types in PostgreSQL. The first one is a plain storage type. The plain storage type actually prevents everything to be toasted or compressed in PostgreSQL. Everything is stored in line with the table. And for the second storage type, it's called extended storage type. Actually, it is the default storage type for the vector data. That means everything over 2 kilobytes will be automatically toasted or compressed in an external table. But as I mentioned, you can't actually compress the vector data. That means for vector data, it's actually equivalent to the external storage data type. And the fourth storage type is the main storage type. So the data in main storage type actually compressed in line with the table. So this is irrelevant to our vector data. So how this impact our query on the embedding data? Let's see an example here. Let's assume we have vector data of 128 dimensions. And then we have about 1 million record here. And we want to query the data. We can see the query planner planned 6 workers here, which is pretty reasonable. And then we expand the dimensions into over 1,500 dimensions. And then we can see the query planner actually planned less workers here. It's about 4 workers. But we are pretty sure we have actually more data here. That will cause our query to be pretty slow. But why this is the case? Because it's over 1,500 dimensions. It is over 2 kilobytes. It will be automatically transformed into a toast internal table. The query planner actually will see less data here. That's why it have plan less worker here. To solve this issue, there's two ways. The first way, you can actually use the plain storage type, and to prevent everything to be toasted. But the limitation of this is you can only store up to 2,000 dimensions data here. So another way is actually you can use a parameter called mean parallel table scan size, and you can set that to a very low value. If you set that into 1, actually the query planner will plan more workers here, which is exactly what we wanted, and that will accelerate your query significantly. Another best practice is about the index strategy. The index strategy actually is related to the approximate nearest neighbor search, ANN here. So ANN, you don't have to search over all the vectors in your database. And it's much faster than the exact nearest neighbor search. But that comes with a cost. So you can't have a 100% recall. Instead, you have about 80% or 90% recall instead. And there's 2 index you can use for ANN. So the RVF flat and HNSW. So the RVF flat is a k-means based algorithm, and the HNSW is actually a graph-based algorithm. The RVF flat organizes the vector data into some kind of a list, and the HNSW actually organizes data into graphs, similar to a B tree. And to build an index for RVF flat, you actually need some pre-populated data. You can't start with some empty data set. And in comparison with HNSW, actually you can start build from an empty index graph, and you keep insert the index iteratively. And the insertion time for RVF flat is bounded by the number of lists it has. And for the HNSW, the insertion time actually increase as the index graph grows. So the takeaway is, if you want to perform exact nearest neighbor search, you don't need any index. So you don't use any index. And if you want a very fast index, you just choose RVF flat as your indexing method. But if you really want to use something easy to manage and also have very high performance and recall, you can choose HNSW index method, which I will deep dive a bit here. So for building the index for HNSW index, so you only need to be aware of 2 parameters here. So the first one is the M. So the larger the M, the more likely you can build neighborhood that have vectors most similar to each other. And the second parameter is called EF construction. So think of EF construction as a memory when you are building the index. So when you are visiting all the vectors in the index graph, you are keeping a list of vectors that are most similar to yourself. So the larger of the list, the more likely you will build some you will find the vectors that are most similar to yourself. So the best practices for building the HNSW index is using the default value, m equals 16. If construction equals 64, is OK. So it usually works. So I will tell you how to tweak that in a few slides. And also, to accelerate your index building process, you can actually use concurrent worker to accelerate your index building. Now we see the parameter for the query stage. So there's only one parameter you need to be worried about, is the EF search. So EF search is pretty similar to the EF construction. It's a memory when you are query against the vectors. And it's a list you are keeping that's most similar to yourself. And the larger this number, the more likely you will find the vectors that are most similar to yourself. A caveat here is your EF search must be greater than or equal to your limit you are writing your query. For example, if in your query you set limit to 10, your EF search must be greater than or equal to 10. Otherwise, your returned record will be less than 10, which is probably not what you wanted. And the best practices for the HNSW queries is, first, you can tweak your query performance and recall during the index building stage. In other words, index building probably has the biggest impact for your query performance and recall. So I will go through that very shortly. Another way to tweak your performance is you can increase your EF search to increase your query recall, but that will decrease your performance. I think the better way to tweak your query performance is in the index building stage. You can actually tweak the M and EF construction parameters here. As shown in the chart here, actually increase M or increase EF construction actually will increase your query recall. But that will also increase your index building time. So a trick here is always start with the EF construction first. This is because compared to increasing the M, increasing EF construction will have a less increase on the index building time. So the takeaway is try the EF construction first and then M. Yeah, we went through a lot of content about the best practice of using PostgreSQL and the pgvector. There's still some other best practice because of the limited time here. We can't go through them all, but feel free to ping us offline to learn more about that. So let's go back a little bit high level and see some bigger pictures here to see how this would actually benefit to your business. So how you can benefit from building a IG application for your business. Let's start with a real customer story here. So this is an anonymous NZ-based customer in the financial services sector. This customer has a lot of internal policy documents inside their company. So their staff spend a lot of time trying to find answers to their questions in those documents. So they spend a lot of time each day. So the company actually asked AWS to build an IG app to help them to accelerate this process. Actually, we built an IG application using the PostgreSQL as a vector store. After we successfully building the app, we actually reduced the answering finding time from 2 to 30 minutes to just 1 minute. So that is a huge boost in their working efficiency. So think about how you can apply this to your use case or to your business. I think the possibilities is unlimited. I talk a lot about PG vector. I talk a lot about the PostgreSQL as a vector store. Actually, this is not your only choice or your only option on AWS when you are trying to build a vector store. Actually, on AWS, we have plenty of options you can use for building your vector stores. So for example, if you already host your data on an OpenSearch system, you can use the vector search functionality on Amazon OpenSearch service. And if you want to do some vector search on a graph data, actually you can try the Amazon Neptune database service or the Amazon Neptune analytics services. And if you try to build some vector search along with the in-memory database, you can try that on the Amazon Memory DB for Redis. And lastly, if you want to build something using NoSQL database, actually have a look at the Amazon Document DB, which you can try some vector search on Amazon Document DB for your NoSQL database. And I think you can choose the right vector database for your use case on AWS very easily. And I talk a lot with technical staff here. I think it's the time to get our hands dirty to build your own applications using the vector store. And you can build your IG applications by yourself. And don't forget to redeem your free 7-day trial of the AWS Skill Builder. And you can try to bring the impact into your business from today. And don't forget to give us some feedback on the mobile app. And your feedback is very important to us. And if you really like our session, please don't hesitate to scan the QR code on the screen now and give us a 5-star rate. And really appreciate your feedback and to help us grow. And now you can enjoy your drinks and the rest of your summit. And thank you very much.